All right, time for another DraftPhysics.com, DebatePhysics.com video presentation. Yeah, another one of those. So anyway, I blocked the whatever his name was guy just because. Yeah, I read the first sentence and he said you had no reason to change the blah, 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 Newton's blah blah blah. So it's just evidence that yes, you people really just don't care about anything to do with the truth. And it's such a simple example that yes, I'm going to provide it once again. So you're doing something very simple. You're just dropping something 15 centimeters, okay, a tiny amount of distance really, and that's not showing up. So I have to fix that. Oh, it's always something. There it is now. All right, so it says tiny amount of distance. So you can imagine if I dropped 1 pound, like one of those little tiny barbells or something, and I dropped it 15 centimeters, it's not going to weigh more than 4 pounds, something like that. So it's a nothing event. All right, and the simple argument is that what he came up with. So the fact is, if this object was in this case 44 grams is what it weighed. Okay, so I mean it's you could argue, okay, that 44 grams is almost a half Newton, okay, but it's really just 0.44 newtons because a Newton is 100 grams. So pretty simple to do that simple equation. Now, so that's its weight, okay, and when it hits the scale, right, the scale is going to, his reading for his pressure sensor was 32, okay, and in newtons. So obviously I did not increase the 44.44 newtons into 32 newtons. I did not do a 64 times its weight. So if I dropped 1 pound, it's not going to hit my hand after 15 inches and weigh 64 pounds. That's totally idiotic. So we know there was something broken, and the simple broken is this decimal place should have been here, and that would have fixed it. Okay, it's 3.2 newtons. All right, so you've taken like a half a stick of butter and you've turned it into 3.2 sticks of butter. A substantial increase in its weight, but not an insane one. So if I drop you 15 centimeters, you can figure, yeah, you're going to probably weigh 5 or 6 times your weight. You're going to hit the ground with a lot of weight, but you're not going to weigh 64 times your weight. So that's silly. All right, and then I demonstrate how it's perfectly consistent with what I've basically argued, that you're moving 1 mile an hour, okay, when you weigh your weight. So if I move you at 1 mile an hour into a scale on its side, you will weigh, okay, you will read on your momentum scale, right, your momentum reader will tell you what your weight is, and your weight is essentially your momentum. And so no matter what object I put here, big or small, if I move it 1 mile an hour, it's going to weigh its actual gravitational weight. So the idea is that we're all sitting in gravity going 1 mile an hour into the earth, essentially to weigh our weight. And the simple argument is if I raise you 1 centimeter, okay, I double your weight. So that's all you have to do is go 1 centimeter up and you'll weigh twice as much as your weight on the scale. Your impact will be twice as high as your actual weight. So with 1 centimeter, 44 grams turns into 88 grams. Okay, not too complicated. All right, and so then if I rise it 3, and I go 4 units of distance, that is 3 more units of distance. So now I'm 4 units of distance above the scale. All right, whoops. I will have doubled that weight. Okay, it'll be double that weight. So 88 becomes 160. Okay, well, no. Jeez, 176, right? 88, 176. Yeah, that's right. Gets tough when you're old. All right. So now I'm at 4 centimeters. Okay. And then I quadruple that. So we're just doing the 4 times the distance to double your velocity and double your weight. Is exactly how it turns out. So as I pointed out, so if I go 16, now he did 15, all right, because I guess he doesn't really understand this concept, so he would have chosen 16, I think, if he knew this is how it actually works. But anyway, so we're a little short of 16, and the expectation would be that I've doubled this number again. So 17, 176 doubled, okay, would be 52, right? 352. All right. Okay, whoops, 352 without any dot in there. And 352 is pretty close to 3280, whatever it was. So it was 32.8 or 6 or something. Anyway, so you can see it's pretty close. All right, not exact, but pretty close. And, that matches what my expectation would be for how it should work. And there's nothing I did here that's cheating or criminal. You just notice an obvious error. I mean, the obvious error is 15 centimeters is not going to make you weigh 64 times your weight. It's just idiotic. And it does work out quite consistent that 15 centimeters would produce what amounts to 8 times your weight, something like that. I should do 44 into 32, but something like that. So that makes perfectly logical sense. That's the argument. It's perfectly reasonable, and it fits, and it works. All right, so I guess I'll call that video for now. Maybe I'll come back later to see if there's something else I want to talk about. No other comments, and it's just there's no point in having a conversation with people that, again, just can't engage in the argument in any kind of fair or reasonable manner. I did nothing unreasonable by pointing out, obviously, the ball does weigh 44 grams. It's very unlikely the scale was way off and the ball really is light as a feather. No. So we know the scale read right, and the pressure sensor has every indication that it read right in the sense that it got a nice curve and all that kind of crap of the pressure. And so clearly the only thing wrong is the fact that it wasn't in newtons. It was a decimal place off. All right. But it's probably just no point in talking to people. They're just, but it should be understood, the video's 10 years old and nobody noticed. I mean, nobody cared that, oh yeah, it's 32 newtons, 15 inches, 32 newtons. They just didn't even notice that, well, that's, that can't be right. So, anyway, till the next time and such. Oh, I just did remember, I forgot to mention that, I had that 35 number, and it was 32. We have to remember it's 1 centimeter less, okay? So it's almost, 8% lower, so the 8% lower would be 32. So I forgot to mention it. I was giving you the numbers for 16 inches of fall, and he only did 15 inches. So obviously, that's the little difference. Now I'm back later and such. All right, so there is another comment here. So it says, a quick change in motion requires a large force because the time is so short. So again, this doesn't mean anything. There's only weight, okay? And here your next sentence is, the weight of the object stays the same, of course. No, the mass of the object stays the same. And you really have to understand the weight is the momentum. So, maybe I'll draw this. Maybe I'll do that. So that's the argument being made, is that all you can do is take a mass, any mass, you take a mass, and all you can do is move it. So if it's a light mass, you understand, doesn't take much force. A heavy mass is going to take a lot of force to move it at the same speed. My hair's all wet. Anyway, Well, that's all it has. And so the simple argument has been made over and over. There's two things that can happen, right? If you're going to hit a fragile surface, I mean a surface like glass or a human brain, okay, that if you hit it with a lot of energy in a short amount of time, that is a high velocity, so it's a light object, but it's moving very fast, it will fracture the pieces. The object will not absorb the energy. The energy won't move into the object, doesn't have enough time to move into the object to be spread around. So it doesn't get spread. Instead, it just starts fracturing the connection between the atoms and it makes a mess of the surface. It's not more energy. And then I could make the opposite example of the brick wall like I did, and you can shoot all the bullets all day long and you're not going to knock anything over. And all you need is one heavy object, banged into it at one time. All the energy is happening less quickly, a lot less quickly, but it's way too much energy for it to absorb, and so the whole wall falls over. It does go into the whole substance because it's not happening too fast, but the faster it happens, the more likely it's going to knock it over anyway, because it's a greater amount of total momentum. But there are circumstances where the recoil of the gun, so to speak, will do more action. Okay, it'll knock something over, and the bullet won't, because the bullet fractures the surface and goes through. So you can understand that it's a condition of how quickly the energy goes into something, and there's no easy term you can use for the difference between light things going fast and heavy things going slow. I mean, there's not some, you can't do any kinetic energy momentum kind of word to describe the two circumstances. We don't have something like light energy and heavy energy. And maybe that would be the smarter way to do it, to understand our fast energy and slow energy, because it's all the same energy. Again, it's just mass moving. And so I can say this over and over, but you're going to find out eventually that the truth is the force is made of quanta, elements of momentum, and it's moving the speed of light. So each bit of force in the world we exist in is a little bit of weight. Okay, it applies a weight when it hits a surface. And the only issue is whether the weight is absorbed by an object or reflected by an object. Those are the only two choices. It gets absorbed or it reflects. Absorbed or reflects. And that'll decide how much of the energy you can get into the object when a force is being applied directly. And we know that when the force is inside of matter, the fact is that if the matter, if if you have the same amount of mass, then the force is already in the right denomination, so to speak, to just transfer into the new piece of mass. It just slides right over, it goes into this new piece of mass and moves, and all the force just migrates from one to the other. But obviously you can't do those transfers when the masses are uneven, because they're not moving the same velocity. The atoms are moving a different velocity. They have to move a different velocity. So you can't just do this simple transfer of the pressure, because in one case you're taking a small number of atoms going very fast and you need it to turn into a bunch of more atoms going very slow. Sort of drawing that differently, I guess. And so you're taking one atom and trying to make it move 6 atoms. You can just understand that you have to spread the motion over the 6 atoms. So obviously you can't transfer the motion as a uniform speed. You have to transfer it by converting it into a lower speed of atom, and vice versa. And clearly it's almost impossible to imagine, how do you take 6 slow-moving atoms and put the energy into one fast-moving atom? That's the really hard part, to imagine how you can multiply, where they each put their energy into something and make one atom move really fast. Well, that's really hard to do. Hard to imagine how you do it. And so those conversions require a lever or some other mechanism you use to create the circumstances that allow you to do the conversion. But that's how you do the conversion, basically, is you just use a lever and allow your 6 to go their slow speed and allow your 1 to go its fast speed, and solve the problem. So we know all that stuff works. And the real point I guess I'm making here is that we don't need Newton's defined as kilograms per meter over seconds or some other nonsense. It's just a weight. All momentum is a weight. It's just applying a pressure. And clearly the pressure can be a high pressure, a high voltage with low amperage, or it can be a low voltage and a high amperage. So just as we don't really have terms for those two things in electricity, we just say it's 100 watts, right? So we don't have some terminology really for high voltage except to say high voltage, right? But we know that high voltages can have very low wattages, and we know that low voltages can have very high wattages. So we know that there's probably needs to be better terminology for, see, we call something static electricity, and so usually static electricity implies a very high voltage and a very low amperage, but it isn't necessarily, okay? It's just that that's the common. So it's really, the science has failed in so many ways, but the fact that they have 17 million different ways to say energy, I mean horsepower, Kelvin, all the temperature scales, all this stuff, all these different ways of saying exactly the same thing. And what it comes down to is it's all just pressure. It's all just weight. It's all just momentum. There's nothing else happening in the universe. And it's just that we don't have good terminology for momentum in the form of high velocity and momentum in the form of low velocity, in the sense of heavy and slow or light and fast. But they're the same momentums. It just means that some will do some jobs better than others. So the fact that, it's probably a good analogy for the difference between something having more and something just being faster. So maybe I'll pause and think about that. Well, not thinking far. I've used before the electricity example, and it's probably a good example, except that we don't have great terminology for the different wattages. But the fact is you know the wattage is what matters. That's what you have to pay for. You have to pay to create the wattage. And it doesn't matter whether you use, you convert your wattage. You have a certain amount of energy. You're going to spin something, a motor. You can convert it into 1,000 volts at, a milliamp, or you can convert it into 1 volt at an amp. You can do it either way. And enjoy your, your wattage in either way, and convey your wattage in either way. And it's clear that, it makes a difference, right? So in electricity transmission, it's much better to have a very high voltage, go through the wire, because it doesn't need as many atoms to transmit the electricity, so the wire doesn't get as hot. And if you try to do it at a low voltage and get the same wattage through, well, then you're involving a lot of atoms, and so the whole thing gets very hot. And so it's very easy to kind of understand that the fast motion is good because it doesn't use a bunch of atoms. A bunch of electrons aren't involved when the pressure's high, and a whole bunch of atoms get involved when the pressure's low. And I've sort of analogized that to understanding that if you move something fast in a fluid, you get all of the energy, does a very good job of just moving in one direction. And the slower it moves, the more likely it is it's going to move stuff in these other directions. So the slower it goes, the more atoms get involved. The faster it goes, the less atoms get involved. So you're losing less of the energy if you can get it to move faster. And that's the idea of a high voltage, is that you're just pushing one electron very fast. It moves another electron very fast. And so there's very little inefficiencies. And the lower the voltage, the more likely it's going to push in lots of directions because of the slow motion. There's time for it to affect other electrons because it's not a quick enough action. It doesn't go through the charge field. See, all the little charges have their own little field. If something goes through that charge field quickly, these charges can't move. But if it goes through the field slowly, they will move. Just as with gravity, if you had a heavy gravitational body and you had a bunch of things in space, and the heavy body was going to go by, the faster it goes by, the less these get pulled in. You could see, the less the gravity is going to affect them. So the faster it went by, the less these other things move. So it's the same idea inside of atoms. You're trying to affect just one atom. the faster you go, the more likely it is these didn't see you. Okay, you weren't in their field of force long enough for them to be moved by the pressure change. The pressure change didn't last long enough. And so that's an easy enough way to understand that the high voltage keeps all of the energy moving this way. The low voltage has a lot more energy going in all kinds of other directions. Generally speaking, in this direction. Obviously, you don't push things backwards. So it's all pushes in some forward vector direction. But it's more spread out and diverse than the motion of a fast object. And that's why there's a huge efficiency in using high voltage. And there's efficiencies in using bullets to kill people because of the structures that you can fracture with quick motion. Now that's it. There's not more energy in the bullet. It's just that the bullet can do more point damage, not only because it's hitting a smaller surface area, but also because it's applying the energy quicker than the energy can move through the object to be dissipated. So all the heat ends up in one place, so to speak, and that place melts. Just like the surface of a piece of steel would melt if you shot it with bullets. The energy doesn't have time to spread. And so, you know, it's not just a subtle fact, okay, that yes, you can make things look like it's more energy, but looking like more energy isn't more energy. It doesn't mean more matter was moved. It just means that you moved more in places that you found significant, and you moved less in the places you didn't find significant, the places you weren't looking. All right. Yeah, that should be enough to... I mean, this is what the whole subject is about. It's conventional physics. The smart people, the physicists, haven't really figured out that looks like or seems like isn't is like. And they have to be careful about not making those kind of mistakes. And they clearly made that mistake in the case of energy. They're just saying it looks like more energy, but it isn't. So again, I could go back to the rolling ball thing again and just say that, oh yeah, it just obviously looks like more energy, right? I mean, you have two of identical balls. You roll one at one velocity, it goes this feeble distance and runs out of energy. And then you roll the second one just twice the velocity, and it goes 4 times the distance. Outrageous. So it obviously looks like, hell, look at how much more work it did. It went so much further. But it didn't do more work. The heat in this surface is only twice the heat, because you know this one velocity happens right here. That's one velocity right here, 1v. So this, the energy dissipated here, is just the same as the energy dissipated over this whole surface, because all this happened in the same amount of time. Time. 1 unit of time. And so yeah, you can figure out that this surface is only twice as hot as that surface. You only took the energy, you only took twice as much energy, but it was harder to take the energy when the thing's moving fast. When the thing's moving fast, it's hard for the surface to pull the energy out of it, because it's not making good contact with the surface. And the slower it goes, the more contact with the surface, the more pressure gravity's creating per inch, and the more it leaks its energy into the surface. So you can understand this surface is only twice as hot, not 4 times as hot. There's not 4 times the energy that was converted from this object into the ground. That's what you're doing. You're just taking the energy in this moving object, and when you put it on the ground, you're just saying, I'm going to let the ground take the energy. And that's all that happens. You take the energy that was in the ball and you put it into the ground. You take the energy that was in the ball, you put it in the ground. And it's only 2 units of energy, not 4 units of energy in the ground, proving the ball only has twice the energy, not 4 times the energy. It just looks like 4, but it isn't 4. It didn't take 4 times the energy to make it go 4 times the distance, because your mechanism for taking the energy out wasn't linear. When it's going fast, it took less energy out. When it's going slow, it took more energy out. And the fact of this half the speed 3/4 of the way down the track proves the point. But what's the point in making these arguments? You are impervious to logic. You have proved it over and over again. And you wish to remain stupid in a belligerent manner. Yeah. And I can't do much for that. I can just do my part. I can't be reasonable for you. You have to learn how to acquire that skill. And such. Alright, I did get another one of these drone comments. And it's just irritating. But maybe email me if you have some drone news, okay? Don't bother making comments about this isn't the drone channel. And I've already made my point that this is more evidence of how people are just completely unscientific. So, it just seems obvious to me. You can tell all kinds of stories of, law enforcement says they observed something, and some guy at this office said something, and some military base said something. I don't first believe that, frankly. That all sounds like hearsay. And on top of that, all of it is dependent on there being some kind of evidence to present. And the fact is the evidence absolutely sucks. And, that's just, I think you have to concede that, yes, this evidence is evidence of nothing. I mean, they can't produce any good images of anything. It's just, there's just no reason to believe this is a real thing. That there's any kind of real anywhere in this subject. There's no, you can't be saying, oh, yeah, we followed a drone and we did this and we did that, but, oh, yeah, nobody turned on their camera. And especially if they're out looking for drones and they don't have cameras and they're looking for drones. Yeah, please. Too silly. So I'm just saying the arguments have to be a little better than this. So, okay, thank you, but no thank you. I really don't want to talk about drones. And if you need to talk about drones, email me. And I still probably won't give a shit. Because it's really not a real story. And the real story is, after all this other fake news, after this preposterous whole election process, all of this other bullshit, you're going to be distracted by this kind of nonsense? You don't think there's something a little more important going on? It just seems like, this almost seems like some sort of engineered plan, to keep people off the subject or something. It's a little too silly. So, thanks, but no thanks. You can't, people, I want to talk physics. I really do. I don't want to talk about shit. The other shit. There's no winning here.